All right, welcome all. Welcome back to the ML+X forum, the spring edition. My name is Chris Endemann, and I work as a data science facilitator at the Data Science Hub, and I also help lead the ML+X community. Today's topic is called Learning Through Comparison Use Cases of Contrastive Learning. And today's topic is going to be split between Yin Lee and myself. So Yin is a assistant professor in the BMI department, and he knows lots about contrastive learning, myself. So we're happy to have him here joining us today. All right, so jumping into contrastive learning. Just a quick show of hands. Who here has heard the term contrastive learning before seeing my email announcement? Okay, a handful of you. Cool. So here's a chart showing you kind of how much interest there's been in this term contrastive learning over time. This is the Google search trends, and it's showing from 2004 up until the present. And then it looks like right here at 2022, things really skyrocketed and we've just continued to grow. So clearly this is a trending topic, but we're not just here because we follow the trends. Contrastive learning has a lot of potential in various kinds of machine learning use cases, whether you're doing clustering or out-of-distribution detection, or you're doing multimodal learning. Today, you're here to find out all about these different applications. So that's all I have to say for now, and I'm happy to hand things off to Ian.
All right, thanks, Chris, for the introduction. And we'll spend the next probably 35 minutes to really go through some of the technical components of contrastive learning. We have a small number of people here, so I would hope this section to be a little bit more interactive. So if you have any questions, feel free to raise your hand. Now, disclaimer, part of these slides are from my course. So if you feel like there's a certain part that is too technical, please let me know. Now, as you probably already know, the kind of a driving force and the key workhorse behind the success of modern machine learning is so-called supervised learning. Now, in the standard supervised learning setting, now before we dive into contrastive learning, let's look at some of the backgrounds. Right. So in a standard supervised learning setting, we really have three things we need to worry about. We need to define the problem, right? What problem we're trying to solve. We need to collect the data and their labels. And then we're going to train a model, right, using the data and labels that we have collected. Now, let me go through this process in case you're not familiar with this process, using this very simple example called image-based object recognition. Now, here, the task is that given this input image, we're going to recognize what is the concept objects that are presented in this image. Now, again, if you look at this problem, you say, look, so we can convert this practical problem into one of the standard machine learning setting. So this is a classification setting, while the output are categorical labels of these object categories, and input are these nice looking images. So that's the first step of problem definition. Now, in the second step, we're going to spend a lot of manual work to collect these images that we have internet. We're going to collect these images from internet and ask people to label them. A lot of work, right? So you're going to present this image and ask a human annotator what object or what concept lies within this image. Now, once you have collected a sufficiently large enough data set, for example, ImageNet with 1.2 million images, now we can train a machine learning model. Nowadays, we talk about machine learning is most likely to be some sort of a deep neural network, right? So you're going to feed in these annotated data into this neural network, and this neural network, during training, look at these images and try to mimic the human labels or the labels provided by human. Right? Now, once you have trained this model, you can evaluate or deploy this model to recognize those unseen images. Now, supervised learning works really, really well. It's behind many of the success of the AI systems, including some part of the model chatbot like ChatGPT and so on. But that's not the full story. So what's going on there is that supervised learning can scale pretty well into a large scale data set. We can do this on ImageNet, about 1,000 categories and 1.2 million images. We can do this on a larger scale data set called GFT 300 million images and roughly 20,000 different categories. And some of the more recent data set with 5 billion images and so on and so forth. It works very well and scales pretty well. The only issue is that now we have way more data. right? So it turns out an estimated 800 million images are uploaded to the social media platform on a daily basis, and also 300 hours of videos are uploaded to the social media platforms, right, every minute. And these videos comes with very rich, metadata, including the audio and text and some other type of data. Now, if you imagine we're going to do supervised learning for all these kind of data, right? Now, think about someone's going to annotate 800 million images on a daily basis. That's a lot of work, right? So that's not a sustainable approach if we're going to handle a very large amount of data that we're producing on a daily basis, right? So here's another example, which is not about natural images, but this is about in the field of medical image analysis. I primarily use image analysis as an example. I think Chris will talk about some other examples about the DNA sequencing analysis, because image analysis is my field of research. I love these examples. So here, what I'm showing on the left-hand side or the right-hand side is a so-called whole slide image data. So how this image is produced is that you put a slice of your tissue samples, sample collected through biopsy, under a microscope, and you can get this very nice, very high resolution image of your tissue sample. If you zoom in, you can even see individual cells. Now, how this is useful? This is very useful in pathology, the actual de facto golden standard for many of the diagnosis of the different type of cancers. Now you have this very high resolution image. Now, if you think about cancer cell versus normal cell, it turns out cancer cells within this high resolution image tends to be concentrated in a few local regions. You can think about this is a kind of a gigantic image that consists of many, many local regions or local patches, and the cancer cells are only located in a few of them, not more of them, obviously. Now, it's very expensive to annotate every local region. They got zooming and say, if there is cancer cell here, there's cancer there. It's relatively easy to label the whole slide because you have other diagnostic signals now associated with this image, right? So you can think about this as a different way of having lots of unlabeled data, right? So think about this very high resolution image. And by the way, this 86,000 times 86,000, like we're talking about 8K TV. This is 2 magnitude number of pixels than the 8K TV now on the market. So you can really think about this gigantic image as many, many smaller images, and many of them are not labeled, right? You only have one label per sort of millions of patches. Now, the key research question is, now we have lots of data like these. We have lots of unlabeled data. We have sparse labels like these. So how can we learn useful deep learning models with limited human label, right? So we know that deep learning models are very, very successful, driven by this supervised learning. It does require lots of annotated data, human annotated data, to be successful. Now, can we make it more useful for those domains where we only have relatively small amount of human labels? Now, before that, before we can answer this question, we have to really look at some sort of a definition of what does it mean by useful deep learning model or useful deep neural network. So the way we think about deep learning is that there is this representation learning aspect, and there is this standard machine learning classification regression aspect. Now let me explain this a little bit more. So one of the key problems in any sort of machine learning problem is how do we represent data, right? So the data can be of any format. We have images, which I like, but we have sequencing data, we can have text data, we can have audio, and we can have physiological signals, motion sensor signals, or kinds of data, time series graphs, and so on and so forth. Now, oftentimes these data, the raw input data is of very high dimension, right? So within a single image, we can have a few million pixels. Within a time series data, we have thousands or tens of thousands steps. The question is, can we abstract away those parts of the data that doesn't, or input signals that does not play a major role in my machine learning task, and really represent these input using a very compact representation. Now, sometimes we call this representation, right? Now, a core part of machine learning is to figure out how we're going to extract meaningful features from the data. Okay. Now, one thing I have to say is that supervised learning, like I showed previously, supervised learning using a deep model is doing the so-called representation learning implicitly, right? Somewhere within this deep model, we can learn to represent the data, and some other parts of the deep model we can leverage those features and to classify these images into the categories, or they'll regress certain values based on the features, right? But here, if we only look at this feature representation problem, this problem is generally known as representation learning, right? The goal here is that, given any sort of input data, we're trying to learn some function, oftentimes parameterized by some deep neural network, that map this input into some sort of abstract. So this abstract features can be a vector, a high-dimensional vector, or some sort of a 2D feature map, which is a bunch of vectors that represent different location or local regions of the image. Right. The hope is that if we have really good representation of the data, right, so if you can represent this image using a small set of numbers, like a vector, now we can attach relatively simple models to support very sophisticated tasks. Right. Think about we can attach really great features, right? Now we can attach a simple linear model on top of the features to classify those object categories, to recognize what object concepts are presented in the input image. So that's the hope of representation learning. So now, like I said, a part of representation learning is implicitly done in the supervised setting, right? In supervised learning, you can do representation learning, and learning is part of the supervised learning set. Now, what if we don't have labels, which is key to supervised learning? Now, a family of method that really looks at so-called self-supervised. So here's the key idea. The key idea is that maybe we don't really need humans to label these data, but rather we can look at some of the patterns, statistical patterns, right, or structures of the data in order to derive or learn these representations. So it's still supervised because learning this representation requires access to the raw data, which is unlabeled. It's called self-supervised in the way that we're exploring the data structure or the regular patterns within the data without the need of any human labels. And here comes contrastive learning. Contrastive learning is a special type of self-supervised representation learning. So it's about the majority part of contrastive learning, where the initial idea is really about representation learning. How can we learn to extract meaningful features by looking at the data itself? And it's so-called self-supervised in the way that we only need access to the raw data without the need of human labels. So, self-supervised representation learning. Any questions so far?
Yeah.
Yes.
Back in your slide where you had your full slide mythology image, you talked about there's at the whole slide level, you might have a label. This one is a certain kind of cancer. In order to do this, you have to also provide slides that definitely are negative. As part of the contrastive learning input, that you say, okay, there's a million slides that are all positive. You need self-supervised learning to figure out which regions are which. But in order to do that, does it also have to, here's a million slides that are definitely not cancerous?
Well, so yes and no. Okay. Now, I have a few slides to talk about that particular example because we have done some work on that. So we can maybe delay part of your question there.
Okay.
But the short answer is that contrastive learning itself does not really require labelable data. Really just, in terms of this pathology image, we're really just look at the local patches of images and trying to compile these local patches in order to derive representation. Now, in the second part, as we're showing here, right? So after we have this meaningful representation, we do need to build some sort of models in order to classify these whole slide images. And there we do need humans to build these simple models, this labels, to learn those features we do found. So that's the short answer. Now, that really, Any further questions? Okay, so that really will prompt me into, introducing the key idea of contrast learning, which is learning to compel. How does it work? So it sort of builds on this very simple intuition that humans, right, you can look at these images and say, if they have similar, semantics. To be more precise, here we're showing this image recognition example. So similar semantics really means same type of objects lies in this image, right? The same object categories, right? Now you can look at this pile of images and say, are they similar? Similar in terms of semantics or, in terms of their object concepts. Now it's pretty obvious because the right image really just a noisy version of the left image, right? So yes, similar. Now we can slightly change or modify the pile and show you the following two images and say, ask the same question, are they similar or not? Right, now if you really look at this right image carefully, you will realize, okay, this right image is really just a manipulated version of the left image. In fact, if you flip horizontally the left image and crop the dark region, or crop the center region of the image, you will see that's the right image. Right? Now it's fairly easy to say that they're similar, right? So the origin and dogs. Now, if you sample a random image instead, you have a very large scale data set, you just sample another random image. Let's say you happen to sample this cat image. Now, it's pretty obvious to say, okay, look, so they do not look similar, or with very high likelihood, if you randomly sample another image from this data set, like, you won't be able to hit a different object. So they're very, very likely to be different, right? So now think about this process. What we're saying is that you can take an image, you can manipulate the image in a certain way, so that by design, the manipulated version of the image will have the same concept as the original image. Now you have some sort of a positive pal you can compel, right? So this is about positive pal. Now you can also easily construct a negative pal by sampling yet another image from this large-scale data set. And very, very likely, you won't be able to hit the dog. Instead, we'll hit something else like cat, grass, shell, and so on and so forth. Right? Now, yes.
How big of an issue are false negatives in that sampling strategy? Like, has there been any work done to see, like, at what rate those false negatives start to become a problem?
Yes. So there are some work on that. Now, so there's two kinds of work. One is, trying to study, the false positive rate. Right, to what extent the false positive rate become a problem in terms of constructing those, algorithms. There's also some work trying to quantify what's the ratio of false positives in real world problem. Now, the latter is typically not a major concern because false positive rate is really low if you have a very large scale data set with lots of concepts. The former is more into the, the kind of a theoretical justification or theoretical insight for those contrast methods. Any questions? Yes. So that's really a key idea. If you want to summarize this idea in a more sort of formal way, is that so contrastive learning is really about learning to compel data. And by learning to compel data, this method or this paradigm really construct two types of data pairs. One is so-called positive pair. Now, oftentimes, positive pair is generated by augmenting or manipulating the input. Right? You take the input x, you can manipulate or augment the input into x plus, so that x and x plus must have the same semantics. And then in this case, we call x and x plus the positive pair. And then same idea, we can easily sample so-called negative pair. Right? You take x and you take any arbitrary data point within your data set. If your data set is sufficiently large and diverse, right? So it's very likely this x and x minus in this case will form a so-called negative pair. So again, positive pair means this input, the two inputs are similar. Negative pair means they're not similar or very high likely to be different. Right, so that's a key idea, right? So now if we can train some sort of machine learning model such that the machine learning model look at these pairs and see, okay, this is positive and that one is negative. following the construction of this, this the key idea here, right? Now that's really the core component of contrastive. Now, one thing I have to mention that contrastive learning stands for not a single method, but really a kind of a range of different kinds of methods, right? Now, here, what I'm going to do is that I'm going to really go through this very early work where now we consider 4 years old as early in the field of AI where everything is evolving really fast. So this is one of the sort of a seminal work that really shows that you can do this contrastive learning. You follow a simple idea, you can be very, very successful. So this paper is called The Simple Framework of Contrastive Learning, or SimCLR in short. So I'm going to go through the simple framework as a way to really illustrate, the key idea and some of the technical components, right? Now, again, we start with our, nice looking dog image, right? And we're going to define, in this case, a set of data augmentations, right? So in the hope that after these augmentation, right, we'll still get an image that looks like the input, where really we're going to get image that conserve the semantics of the input or the object category in this case. Now, some of these are pretty obvious. You kind of flip the image, you crop it, you block some non-essential part of this image, you rotate it, you add some noise, you add some blur, you add some color variation, and you sort of try to do an edge detector, right? That gives you the contour of the dog instead of the actual dog, right? Throw away the details. Right. So you can think about, we have a large set of, so-called augmentation, we tend to call that augmentation, or manipulations that are manually designed so that we can really preserve the semantics of the input. Now, what happened here is that for any sort of input image, this SimCLR was originally demonstrated on image data, so that's why we're using the stock image as an example. So given the stock image, we can randomly sample these augmentations and generate a pair of images, right? So these are augmented version of the dog. So it's a noisy, kind of slightly more noisy version, and this offloader, right? But essentially, they're still the same object, right? So the core concept is to ask a machine learning model, or really to task a machine learning model, and tell this model that these two images are similar. They're of the same concept. And thus, if we're going to learn some sort of representation of these two images, they should be similar in some sort of abstract way, right? So the key idea is that, look, so what we're going to learn is some sort of f function or f of theta function that maps this input image into some representation. Right, so here we're slightly abusing the symbols. We call these H, right? So we have HI and HJ. So HI will be a vector representation of these noisy image, and HJ would be a vector representation of this uploaded image. Now, so the key idea is that if we generate the classifier like this way, right, these two representations will be similar. So if we design some sort of similarity score between HI and HJ, which I'll explain that later, we would hope that these two vector representations will have very high similarities. They will be similar. Now, similarly, we can construct the negative pairs as we described previously. You take, one augmented version of the image, you take another image, another random image, sampled from your data set. Now, with very, very high likelihood, you will hit a negative sample. Right, so I already explained the question here, right? So why you can just randomly sample from your data set and get a negative sample. Right, now we do the same thing. We do apply the learned or the feature mapping F, right? So we have the noisy dog is HI, and in this case, we have this cat image is HJ. Now we're going to use the same sort of similarity scoring function. The only difference is that in this case, we expect their similarity to be valuable. They're going to look very different in this feature space. Right? So that's really the key idea, right? Now, in terms of design, we can slightly look into the more the technical details here, right? So you can have this f function which is realized using a deep model that takes the image and maps out a vector-based representation, right? So HI and HJ. Now, in this case, we have positive pairs and negative pairs, right? So positive pairs, we hope that HI and HJ will be similar, and negative pairs will be dissimilar or different in terms of similarity scores. Like you have a pair of dogs, you have high similarity score, you have dog and cat, you have those things. Now, how exactly it operates is that it relies on an additional projector step. So this G of X is a projection that further projects H into some very low dimensional representation phi. Why do we need that? Okay, so here's the key intuition. So eventually, we're going to build some very simple score function, right? Now, we know that a simple score function like the precise similarity or dot product or Euclidean distance, or those kind of similarity metrics does not work very well in high-dimensional space. You think about, the high-dimensional space is kind of weird space because things are equally far away to some extent, right? So, some of the intuition we have, let's say cosine similarity measures, the angle between two vectors, right? Or Euclidean distance measures the distance between 2 points. Those intuition works really, really well if you have a relatively low dimensional space and stops to work if you have high dimensional space. I'm not going to unfold there, but you can think about that as a known, very interesting phenomenon in statistics. So what we eventually want is that we want some sort of a Z, which is of lower dimension, so that we can apply relatively simple metrics to measure their similarity. In this case, we're using the cosine similarity to measure the intersecting angle between the CI and ZG in this particular case. But this projection function G is actually important because if we directly apply, those metrics over this HI and HJ, those high dimensional vectors, it doesn't work. Refer to the paper for more details. I'll refer to the paper for more details. Right. Now, the final step is that after projection, you have this low dimensional, right? So by low dimensional, we're talking about 64 or 128, something like that. Basically less than the 100 dimension vector, right? So there we're going to compute the similarity score and try to maximize, so-called maximize agreement. So the exact details goes with a bunch of equations and eventually lands into this thing so-called contrastive loss or inference CE. But at a very high level, you can think about this loss really trying to do the following, right? Now, if you look at a pair of low-dimensional representation from a positive pair, you're going to ask the model to output, yes, they're similar, or 1. If you're looking at a pair of negative pairs, right, or negative pairs, you have Zi and Zj, you compute their similarity score, you can ask the model to output 0, meaning that they're different. Right. So at a very high level, this maximum agreement really just means some sort of binary classification, right? You ask the model to look at these low-dimensional representations, right, and their cosine similarity and say, okay, now tell me if they're similar or not. So that's a key idea. So I'm not going to expand the details because I think, if you're actually interested in this, I put the reference underneath the slide, I think. Right. So here are some of the technical details. If you, sort of lose track on some aspect of that, that's totally fine. Because the key component is that we're going to learn some sort of function F that really trying to represent, the input data in a meaningful way. Right. So that's the key part, right? So by constructing those positive pairs and negative pairs from the data itself without some of the human labels, right? So we're going to try to learn this function F that maps the data into some sort of feature representation. Now, from a more practical or computational perspective, this training does not require human labels, but does require lots of unlabeled data in order to build these representations. And because of that, this training can be very, very computationally intensive, right? We'll see a live example later, but there's a caveat here. Now, once this model has been trained, I think we already talked about this part of that. Now we can really take these features, right? So now we consider this function as already been learned or fixed, right? For any sort of input, we can use function f to map this input into these features, right? Into this feature space. And from there, we can train a simple model, for example, a linear classifier, or a tree-based model around forest to perform the actual machine learning task. Now we call this transfer learning. What it means is that we're taking the feature that we learned and trying to transfer the features into a task, right? In this case, we assume that we often assume that for this task we want to solve, there's only a limited number of labeled data points, right? So by transfer learning, we're going to build out this meaningful feature representation and use a sparse amount of human labeled data to construct the classifier. Yes.
I have a question about like transfer learning here. Just like if we transfer this per-chain model to the downstream task like classification, is this task will influence our contrastive per-chaining. For example, if we specify negative label from dog a cat, but our downstream task is just dividing the images into animals, vehicles, something like that. That might be not a negative pairs for different downstream tasks.
Yeah, I mean, I see your concern here. Basically, you're saying that so the representation derived from contrastive learning may not be well aligned with the representation that is needed for downstream tasks, right? So example you're showing here is instance level, differentiation versus, kind of a rough categorical level differentiation. Now, the short answer is sometimes, only sometimes. There are quite some work understanding the theoretical foundation of contrastive learning, including some of our prior work in collaboration with Yu's group, Yu's group. So the way we think about contrastive learning, I think Chris will touch some aspect of that, is that they're doing implicit clustering, right? Now think about the following setting. You have lots of data. You have lots of fine-grained structure over the data, define those fine-grained categories. Now, what contrastive learning is trying to do exactly is to do some sort of fine-grained clustering. Okay, now, in the hope that if we have fine-grained cluster sort of structure over the data points, we will be able to answer some of the high-level questions, like the species of the animals. So I think that's a key intuition. If you're interested, I can point you to some of the more theoretical aspects of contrastive learning. But the key idea is that you can. So contrastive learning is more about discovering those fine-grained structure of the data, and you can build on top of those fine-grained structure to handle some of the coarse-grained sort of a recognition of the concepts. But you cannot go further fine-grained. So that's the key situation. It's a good question. Any further questions?
Yeah, how about this framework also works for object detection, but just like for all pictures?
Yeah. It definitely works for object detection because, look, so you can basically say, okay, look, so I'm going to learn those features, right? And grab those features and train some simple detection model. So it does work for detection and also segmentation and a few other image analysis tasks, right? So the way you think about this is that contrastive learning provides you good features, and you can build on those good features to support the large range of image analysis tasks. Okay, so moving forward, I think what Synclia does is that it is exactly as I mentioned in this transfer learning setting. What they do is that they train this model over a large scale data set, in this case ImageNet, without the actual labels of these data set. And then they take the features, right? Just consider the features affixed every single image. You now have a feature vector. They then train a linear classifier using those features and probe. They call this linear probe, right? And really examine the performance of this linear classifier. Right, so the start is really how these model the performance of this model stands with respect to other type of self-supervised learning method, right? So 2x and 4x really means the number of parameters, number of model parameters. So basically, as they scale up the model, right? When you have the start on the top right, the performance level is comparable to that supervised learning. So that's the actual important aspect. Right? So all other methods here, those self-supervised learning methods are probably less important. The take-home idea is that you can scale up this, contrastive learning paradigm, and it does provide you really good features such that by building a linear classifier on top of these features, you can have performance that is comparable to a fully supervised setting. Right, so that is really, really interesting. And one thing I have to mention that you could reach that level of performance using a fraction of the data, even though this particular figure shows that it uses 100% of training data, but essentially you're only training a linear classifier, right? So you can use a small fraction of the data to achieve comparable performance with respect to supervised, which is great, right? So, and that's really the motivation of contrastive learning. You can learn meaningful representation, use sparse labels, solve machine learning challenge. Now, some of the recent development, just a very quick slide. So this is simply, we already talked about this idea, right? So you can have some sort of encoders to encode them. Or in this case, this encoder is really the function mapping F. Encoders to convert the input data into some feature representation and compile the feature representation in a certain way. We have this almost concurrent work on ML+X, almost exactly the same idea. Now, the key difference is that they're using an encoder design that is asymmetric. So they're not using, so encoder Q and encoder K simply are the same thing. Basically, they share the same set of parameters. In ML+X, this momentum encoder. So one part of the encoder is similar to simply, and the other part is some sort of moving average of previous encoders. Now, the other thing they do is that instead of sampling a very large set of negative samples, they actually use kind of reuse some of the data samples from the previous training. Again, if you're interested, I think the details will go to this paper. Now, some of the most recent development, I think this is 21, is basically saying, look, so, you probably don't need those very sophisticated mechanisms, right? All you need is that you can stop the gradients for one of the encoder, one side of the encoder, right? And you can do it pretty well. So you can think about this same cell as a much simplified version of, say, CLIA that can still work very well. And they also, remove the contrastive loss so that you can learn from a relatively small or batch size. A little bit of a practical concern. So the vanilla version of the contrastive learning work, basically SimCLIA, on one side of the spectrum, you will need a very large batch size. The reason is that you will need a lot of negative L's to be able to contrast the positive. Now, this is partially alleviated by ML+X, which does no longer require a very large batch size and a small number of negative L's, and eventually sort of solved by this more recent work. They only require a small number of positive and negative L's. Okay, so far what we are talking about for contrastive learning is that we're talking about contrastive learning for image analysis, or really contrastive learning for a single modality. But oftentimes, if you think about the data, again, we take this image analysis, for example, there's always other type of data, right? So data from different modalities or data from the same modality, but some sort of additional information, right? So think about in the realm of medical image analysis, you can have front view CT, you can have side view CT, right? So here we're showing this interesting example I took from our news website. The title of this image is called Spring of Deception. Unfortunately, we don't have snow today, which is, this winter is unusually warm and less snow for some reason. But you can look at this image and look at the text description, and they roughly convey the same information, right? This food delivery robot is making its way through the snow on campus. Now, as you may notice that, the image and the caption associated with the image convey the same information through two different channels, right? Now, essentially, they're the same thing, right? The same semantics, right? You can say, look, so we can apply the same idea of contrastive learning. We can look at signal from modality A and signal from modality B. If they're matching, they'll be similar, right? So in this case, the images and captions will be similar. If they do not match each other, they will be dissimilar or different, right? Same idea, except that now we have different type of function to map the input image to the feature space and to map the input text information to the feature space. We're using modality-specific encoders in this case. So this very, very simple idea really gives rise to this very powerful model called CLIP, contrastive image text, for training. I think I spent more time than I expected, so I will be, a little bit, I make the pace slightly faster, right? So same idea, right? So you can take images and their captions. Now in this case, you already have PALs. You already have PAL data, like images and their matching captions. And you can easily generate, negative PALs. You have positive PALs already, right? So you can easily generate negative PALs by taking a random image and a random non-matching caption. Now, it's very likely that they will be very, very different. Now, what you do is that you're going to collect those negative PALs and positive PALs, right? You're going to construct the similarity matrix, only the matching ones. So here, the matching ones means the ones on the diagonal will be labeled as 1. All the non-matching ones will be labeled as 0. So basically, you take the image, encode them into a bunch of feature vectors. You take the text or the caption, encode them into a bunch of vectors. Now you do a pairwise comparison to generate this affinity matrix, while the diagonal elements of this affinity matrix will be 1, and off-diagonal elements will be 0. And that will become the supervisory signal for learning the text encoder image. Now, the important caveat is that this works very well, but only works if you really scale up this training paradigm. In fact, this CLIP model is trained on 400 million images and their captions that are curated from the internet. So this is from OpenAI, so they have a lot of computing resources to experiment or explore these ideas. Now, one of the key design of this CLIP model is that they have both the image and text encoder. This allows so-called zero-shot transfer of the learned representation. Now, record that if we only do this in the image domain, what we get is some sort of a meaningful image feature vectors, right? And then we still need some sort of labels in order to sort of make use of those image features. But in this case, if you have additional text encoder that is aligned with the image encoder, now you can do something really smart. Now, let's say you want to construct a classifier for a certain object, say cat or dog, right? Now, what you can do is that you can use the text encoder to encode this concept into a text encoder. Okay. So this text encoder is part of the CLIP training pipeline, right? So you'll say, look, so if I want to recognize, plant, cat, dog, and bird, those, concepts, I'll convert them into a sentence to say, okay, this is the photo of a cat, this is a photo of a dog, this is a photo of a plant, and so on and so forth. I'll pass that into a text encoder that will give me some sort of embeddings or features of those text concepts, right? Now I have a feature or embedding or concept vector of cat, okay? Another concept vector of dog, another concept vector of plant. Okay. Now, given any input image, we're going to extract image features, right? So that is that I there, right? Now, what we're going to do is that we now compile this image level features against those concept vectors, right? So if you think about the following, you have this, I can't really see what's going on there, but let's say if you have this little dog image, right? Now, if you compile the image feature against the dog concept vector, you will get a pretty high similarity score. This is by training. It's designed to do this. Now, if you compile that dog image feature against the concept of a cat, you have very low similarity score, right? And in doing so, you're building a classifier for free. Now you have the classifier that basically give you confidence about individual categories by comparing the image features against those text or concept vectors, right? And by choosing the highest responding concept vector over a certain threshold, you can actually build a classifier to say what object lies in that image. So this is what we generally call zero-shot inference. In this case, you don't even need any human labels in order to perform inference, or in order to recognize, to be more specifically, to recognize what object lies in this image. Right, now you can extend this idea across many different modalities, as long as you can do pairwise comparison for the modalities. So this image bind that you're using, they're using the visual modality. The images is a bridge, right? You can compile image to text, you can compile image to audio, you can compile image to sensor data, and eventually you can bind them more together. Right? Like the image data is like the bridge that binds everything together. So I think I already spent way too much time. Just very brief view of pathology images. Right. So I'm not escape the backgrounds. We're out of time. So what we have done a few years ago is that we're taking these pathology images and we're extracting local patches with images and really apply contrastive learning on top of those local patches. Right. The idea is that we take one patch, right, and we take another patch that is far away, so that is an active L, or we can take a patch and a slightly shifted version of that patch, or a patch that is nearby, or some sort of augmented version of the patch. We call that a positive L. Right. Now we can sample many minutes of those patches, those pals, to construct those contrastive learning methods and to derive meaningful representation. And on top of that, we're going to use sparsely annotated slide level labels to classify these whole slide images into cancer versus non-cancer. With that, I'm going to conclude my part. I think so far we talk about contrastive learning as a powerful learning paradigm for self-supervised representation learning. So you can learn from unlabeled data, right? Learn meaningful features from not unlabeled data, and further build machine learning models using sparse labels. And you can do this for a single modality. You can do this across different modalities. Now I think I really need to hand this over to Chris.
Hey, thank you so much for that overview of contrastive learning and its impact, especially when you lack labels or when you're doing multimodal learning. For this last bit of the talk, I want to extend these ideas and talk about how contrastive learning can be used in clustering applications, as well as out-of-distribution detection. So if we think about kind of the standard supervised learning framework of how we train our models, we really give our models a limited worldview. That is, they see a certain number of classes, maybe your robot or your AI agent or your AI is trained to classify cats and dogs. Therefore, it's going to look at every image and say, this is either a cat or it's a dog. And so, we're calling this thing AI, but this is how it views a picture of an orange. It says it's a 51% dog, 49% cat. So this is just by virtue of doing supervised learning, these models have to bin every view observation as belonging to each of the classes that they have observed. Whereas if we look at the contrastive learning models, the model's learning to map similar images closer together in their embedding space that learned feature representation of the neural network. And then it has dissimilar images further apart. So you basically have this implicit clustering process that's happening with your data. And so a contrastive learning model might say, I've seen lots of cats and dogs paired together, and I know what makes them look alike, what makes them look different. So if you were to show a contrastive learning model a picture of an orange, even those trained on pairs of cats and dogs, it would say this is unlike anything I've seen before. The image features do not map to my learned representations of cats and dogs. So this seems like a plus, right? Rather than forcing data into the observed bins or the observed categories, the model can now say this new data point does not resemble what I've seen in the past. So when might this kind of view of the world or your training data be helpful? Any ideas?
I can't answer your question, Brad, but maybe a challenge, or maybe you can educate me on why it's different. So in my project, which is what I presented before, Conformer, I don't do the tradition. I have not implemented the traditional final layer to come up with the bins of the supervised labels I trained it on. Instead, I just have it generate the embedding vector in its 128-dimensional space of the last layer. So I get a number to the category.
Gotcha.
So Euclidean, then I use that to do the Euclidean distance between points that decide what it's close to. It seems like it achieves what you're claiming here is unique to self-supervised learning.
Yeah, what you're just describing, if you were to use the contrastive learning framework on your data, you would most likely see more informative features extracted from the data. Because if you do supervised learning to extract those features from the data, the features that develop are going to be really tied to those classes that you use. Whereas if you use contrastive learning, you're asking the model to then compare data. And so it learns these clusters that separate your data rather than you giving it classes to begin with.
So then my experience, the last time I trained it was in August. I've added a lot of new data, but I didn't train the model on it. But it's still able to successfully, essentially, what maybe any neural network does. It is building a generalized skill, so it's able to classify in terms of just scoring and the Euclidean distance.
Right.
New classes that it was never trained on.
Interesting. Yeah. So it sounds like it's learned a useful feature representation.
Right. Which I'm guessing is probably common in any neural network.
Yes, we're going to touch on that a little bit more in just a couple of slides. So let's get back to that. So what I was trying to get at is clustering. So clustering is one big way that contrastive learning can help us because we don't have knowledge of the class labels necessarily, or we don't necessarily know the number of clusters to begin with. Despite this fact, we can learn a rich feature space of our data using the inherent similarities of our data points, not the label. And this is especially helpful with clustering because the model is going to remain stable even if or when you encounter new clusters in your data. So you can start with a contrastive learning model that's been trained on the majority of your data. As you collect more and more data, you can continue to fine-tune it, and it's going to adapt its representation and take into account those new clusters. So to solidify this, here's one example of doing contrastive learning using RNA sequencing data. So we talked about how images can be trained with contrastive learning. In this example, we have a vector of genes. And the augmentation that we're doing is we're masking different genes randomly. And so we can mask a certain percentage of the genes randomly. It's sort of like masking a portion of an image in the contrastive learning example. And even though we're masking some of those genes, the overall cell gene is going to be the same. So we consider these two samples here to be the same, even though we're randomly covering up specific genes. So it's a very similar idea to images. The key difference here is that the augmentations involve randomly removing certain genes. So what happens if we form a contrastive learning model using that kind of setup? The authors of this paper evaluated their contrastive learning clustering framework on 15 real data sets. And just to cover a little bit of these results, over here is their contrastive learning model, and this RE score is the adjusted RAND index. And so that's giving you a measure of how similar the final clustering result is to the ground truth clustering result. The NMI is a very similar score, but it's a little bit more reliable if you have unbalanced data. The takeaway here is the red bar is the highest, so that's good news. That is the contrastive learning clustering procedure. And then to the right here, we have a couple of other clustering options. These are both using autoencoders. Has anyone here heard of an autoencoder? Yeah, it's another way that you can use a deep neural network to extract a feature representation from your data. So it's kind of similar to contrastive learning, but instead of contrasting examples, you're sending your data through a neural network and asking it to compress your data's representation. I will also point out the silhouette score here is not so great, right? I don't know if anyone here is using the silhouette score, but it looks like this bar over here is the highest, and it actually does not recover the ground truth the best. So if anyone's doing clustering here, I feel for you. It can be a really, really difficult application area. And just kind of adding on to this, this is the simulated data results. Basically, the trends are all the same. The ARI score is going to be the highest with the contrastive learning example. And again, the silhouette score is not so reliable. Yeah, question.
Is the thought behind the masking augmentation strategy just to kind of match that dropout, or I guess the zero inflation side of single cell sequencing data? Was that kind of the thought behind it?
I'm not so familiar with the zero inflation concept that you're referring to. I'm not really in the gene space myself. But I think the idea is you want to keep the overall cell genes the same, and you can still have that same expression of the cell if you mask a certain number of genes. Okay, yeah. Good question. I know I'm over time, so just give me a few more minutes. Runtime considerations. So the downside of contrastive learning is it typically will take longer to run compared to supervised learning. However, if you have high dimensional sparse data, contrastive learning can be pretty efficient. So on the far left there, you can look at the contrastive learning KM bar and compare that to the autoencoders to the right. So these two bars would be the autoencoders, and this is contrastive learning. Since we have high dimensional sparse data, contrastive learning is actually quite efficient here. And that's really because the autoencoder method is going to be very computationally intensive. One other concept I want to bring up is auto-distribution detection. So auto-distribution data, or OOD data, refers to data that significantly differs from the training data on which you've built your machine learning model. This is an image showing what you might imagine the representation of images on the internet might look like in a feature space, a 3D feature space. Whereas this is what you might imagine the CIFAR-10 dataset to look like in this 3D space. Have folks here heard of the CIFAR-10 dataset? It's a really popular image dataset that contains, I think, 100 natural classes or 1,000, and it's very large. So why OOD data matters? Models can be overconfident when presented with auto-distribution data, leading to inaccurate predictions. So in certain application areas, such as healthcare, maybe you've trained a model from data from one hospital, and you're trying to apply it to another hospital. That data or that model might not predict so well when you apply it to a new hospital's data set. And then we have autonomous vehicles, insurance, legal contexts. In certain areas, if you're not taking this into account, this risk of auto-distribution data, you can end up with serious consequences. So distance-based OOD detection is when we try to measure the distance between in-distribution data and out-of-distribution data, and we use that distance to set a threshold that allows us to reject out-of-distribution data. So what should we use as a feature representation of the data to measure distance? Any ideas? You can use the raw data itself, or
Whatever your representation is.
exactly, we'll use a neural network to actually learn that representation. Because neural networks, their general property is that they learn hierarchical feature representations. So here we're looking at a neural network that was trained on image data, and the first layer is learning to detect edges in the images. The second layer might be learning to detect like ears or eyes or noses, and the third layer is detecting different kinds of faces. So we're going to leverage this fact, and we're going to look at the representation in the last layer of our trained model, and we're going to use that as a feature representation to then measure distance between ID data and OOD data. Now, what happens if we try to do OOD detection, distance-based detection, using a contrastive learning framework versus a supervised learning framework. So here are some results. Unpacking this for you. This is looking at the CIFAR-10 dataset as the in-distribution data. And then the x-axis here is indicating whether or not these other examples, like a leopard, is close to the CIFAR data representation or far away. So when the OOD data is far away, you would expect to be able to distinguish OOD data very easily. And when it's near, you would expect the task to be more difficult, so lower on the y-axis. Now, if we use contrastive learning, you can see that the red points are much higher on the y-axis, indicating that we can separate the ID data and the OOD data more easily. And this is comparing to a supervised learned framework. Similar data is over here. The red bars are going to be OOD data with contrastive learning, the gray is without, and the blue is the in distribution. So you can see that the red and the blue are more separated than the blue and the gray. All right, I know I'm over time. I just want to end with one last thing. We've talked only about a couple of ways that we can represent pairs of data using images or gene sequences. There are many other possibilities. So if you're working with graph data, you can augment your graphs and use that to generate your pairs of data. If you're working with tabular data, you can corrupt different columns in the tabular data set and use that as your augmented views. If you're working with enzymes, these authors paired up enzymes that had similar functions and use that as a positive pair. And if you're working with time series, you can do augmentations, or you can try to find out which time periods are similar using some kind of pre-processing algorithm. So just to give you a little bit of sense of what is possible in this space. And then I'll just end with check our Nexus website in about a week. And here's the link to that website if you're not already familiar with this platform. We're going to be posting a couple of notebooks that show the impact of clustering when you use contrastive learning. And then I'll also be posting other contrastive learning talks that have been recorded on campus. So I think we'll end there, but thanks all for joining, and I'm happy to stick around if anyone has any last questions. So yeah, Al.
Is the research on based on slightly similar to questions somebody asked before? What is the minimum diversity of the input data set in order to get good results?
I think you want to think about it as the contrastive learning model is going to learn a representation of whatever data you give it. And so, yeah, I don't know. Yin, do you have any thoughts on this? Like how?
I mean, so I think there's a theoretical aspects in terms of how we quantify the bounds and stuff like that. So practically, I think, at least for imaging data, we do observe that you will need a pretty large data set. Like if you recall the CLIP model, the key success of the model is being able to train out, 400 million images. Some of the early version of contrastive learning, like Simplia, was demonstrated on about a million images. I think that's roughly, what we will expect for image data. The hope is that you can get a lot of these labeled data and then just train these models to derive the particular features.
Yeah, I guess I'm thinking of the question of is there a minimum ratio of number of samples to number of classes? Like, for example, if you take the CIFAR-10 set, it's important. Like what you said, is it 10 classes or 1,000?
I think it's 1,000. But I want to check.
Where if it was 10 classes, like would it not be diverse enough?
Well, CIFAR is an interesting data set. So CIFAR-10 have 10 classes, CIFAR-100 have 100 classes. But essentially, they're the same data set. So it's the same amount of the same set of images. It's really just the definition of the categories. So I think it sort of depends on, I think your question is also depends on the definition of the categories. Like, are we looking at a particular type of object or looking at some sort of rather rough category I don't think there's a kind of an answer from more empirical perspective. I think it's probably some sort of that trials and errors. You try and see if it works or not.
Machine learning. What do you expect?
Yeah, I suppose it's the same. Is it possible for the data to be too diverse?
I mean, I guess you have to think about your downstream task. So what are you trying to use this representation for? I think if your data was too diverse, I think that could be a risk if you're sort of learning to represent data that's not relevant to your downstream task. That could be a possible risk. But so long as the data still contains aspects that are relevant to the downstream task, that would be less of a risk.
You get back to the usual axiom of you kind of have to know your data.
Yes. You have a question? Yeah.
I want to add something up about the discussion of diversity. In my understanding, a contrastive learning is a support vector machine, like the representation space. It's like you want a fine-grained dataset structure, just put the same label class enough, like clustering, and push different labels away. So if based on this view, the support vector machine, if you have just like 2 or 3 or 4 classes, the central area may have a good boundary, but the outside area, if you don't have enough class or enough labels, they will be arbitrary lines. So the reason we need like 1,000 class, maybe just put dots enough in the whole representation space so that we could have a better fine-grained data structure.
Yeah. I hadn't thought about it in terms of the support vector machine analogy. That's interesting. Yeah.
I think just like contrastive learning in representation space, support vector machine, and word vector, they are actually similar thing. Want to manipulate the representation space to put every data sample into a better position.
Right. Yeah. Yeah. With all the supervised learning frameworks, your model is forced to partition the data into those bins.
Yeah.
And sometimes by virtue of doing that supervised learning process, it may not handle overlapping bins so well. Whereas with contrastive learning, even if the clusters are overlapping, it can handle that nuance. Yeah.
I mean, overgeneralization. I think that other non-supervised learning can also, if you give it enough data, it can handle overlapping bins.
It can handle it, just not as well in general as contrastive.
That's like the graph shows. I mean,
yes,
it's either they overlap
exactly
green and red regions. They can't.
Yeah, I mean,
that's the difference, but they're not.
Classes can overlap if they have one distinguishing feature that could separate them. Then a supervised learning model would have no problem distinguishing those two different classes. But yeah, clearly with contrastive learning, since you are focusing on similarities and you're not trying to draw these hard lines in the data that separate the classes, you get more of a continuous comparison across observations.
Is that graph normalized with computing input, like computing cost?
No.
Just to make sure we're not claiming that the red zone is better than the gray zone, but didn't discounted the fact that you had to put 10 times as much resources into the red zone.
Yeah, the training is in general going to take longer with contrastive learning, which is maybe something we should emphasize more because it's not going to necessarily always be the best solution for you. If you don't have a lot of compute resources, you might want to start with a supervised approach. Yeah.
Thank you.
Yeah. Well, thanks all for joining it. I hope to see you Wednesday, and we'll see you back here next month for our March ML+X.